Hello! It's December 13 and it's time to open a new slot in our Coding Advent calendar. Today's problem is about arrays, which are a fundamental data structure in programming. Let's dive in. Here is a problem for today. Minimum falling path sum. Given an n-to-n array of integers called matrix, return the minimum sum of any falling path through the matrix. The falling path starts at any element in the first row and chooses the element in the next row that is either directly below or diagonally left-right. So it is like specifically the next element from position row column will be row plus 1 column minus 1, row plus 1 column, or row plus 1 column plus 1. So for this case, for this matrix, there are two possible solutions, 1, 5, 7, 1, 4, 8, because both of these solutions will result 13. So let's think a bit how are we going to solve this problem, and let's try to reduce it. So imagine our matrix here, 6, 5, 4, 7, 8, 7, 8, 9. Okay, from top to bottom. Let's consider this 6. What is the best value from previous row? It is 1, right? So let's add it here. For this 5, it is also 1. Let's add it here. For this 4, it's also 1. Let's add it here, it gets 5. And we remove this first row. And next we need to repeat this again. For this 7, it is 6. And we have 13. For this 8, it is 5. And we get 13. And for this 9, it is also 5, and we get 14. And we remove the previous row. Then we just need to scan this last row and check for the the minimum value in it. That's it. That's the whole algorithm. Let's do this. Let's implement it. Okay. So I will create a few helper functions. I will call this function ref. It is going to return the best value from previous row. Okay. We have only 3 options, and we also should consider left and right corners, in which we have only 2 options. And let's do it like this. Let's define a minimum so far. And let's fix it to the value I minus 1, the previous row, and the position right above the current. Now, if I more than 0, then we can consider the previous position in the previous row. Min equal to maths min, and matrix I minus 1 and G minus 1 if it is J, yes, of course. If J less than matrix I minus 1 length minus 1, then mean can be math mean and matrix I minus 1 G plus 1. Return mean. Okay, so we have a function which will return the best value from previous row for any position in the matrix. So let's do this. So first of all, we need to consider one more corner case, which is the matrix of size 1, and it cannot be less than 1, right? So if matrix length more than 1, then we can proceed with our algorithm, because in other way there is no previous row. For int I equal to 1, I less than matrix I equal to 1, j equal to 0, j less than and I will do not a very popular move here. I will not create new memory array. I can create a single dimensional array to store temporary value, but I will adjust the values in array that is our argument. Sometimes it can be possible and acceptable. Okay, plus equal to ref matrix A J. Okay, so we will do this for the whole matrix, for the whole two-dimensional array. And what do we need to do now? We need to scan the last row and find minimum value in it. This is our last row, right? We define the first column in the last row as our current minimum. That's it. So again, what do we do? First we check the length of our matrix, and if it's 1, then we skip this and we go to min in row. This min in row sets the default min value for the first column in this matrix, and if there are no more columns, it will just return min, the single value in a matrix. If our matrix has more than one column and one row, we can go through this algorithm, which will collapse values with our finding function, which will result the best value in the last row, and then we just scan this last row for min value. Let's run it. Okay. Yeah, int yes, typo. And what here? Oh, yes, typo here. Okay, both cases work. Let's submit. That's it. Our solution beats 95% of all solutions submitted. Okay, so here we are. Here we are. And here are everybody else. So let's identify the complexity of our algorithm. If we define the size of the matrix as n, so we need to check every single element of this matrix. And the time complexity will be n squared because we have square matrix. What about memory consumption? In this case, we do not create any additional array. So for this case, it is fixed size, big of 1. But for case when we cannot modify input array, we can create single dimensional array and store all values in it. So in this case, the memory consumption will be big of n. That's it. That's the solution. We have something new. We have arrays. I hope you enjoyed today's lesson on arrays. As we discussed, arrays are very simple yet powerful data structure, but they can also be a source of common errors such as out-of-boundaries exceptions. It's important to be mindful of array indices and understand what your code is doing when you reference the i-1 or i+1 position in an array. Practice makes perfect, so keep working on arrays and continue to improve your skills. We will see you tomorrow for another lesson.